Good morning, good afternoon, good evening. Welcome back to Chapter 36. We're talking about population ecology. Let's talk about survivorship curves. These survivorship curves are trends that different species will, their life history strategy. The percent survivorship curve refers to the percent of individuals that are alive at any given age. It'll make more sense once we look at the picture. Our first survivorship curve is referred to as a type 1 survivorship curve. And a type 1 survivorship curve means that you have very little infant mortality. You have very high elderly mortality. A type 2 survivorship curve means that individuals had roughly the same chance of dying or surviving at any life stage. And last is type 3. Type 3 is extremely high infant mortality rate with a very low elderly mortality rate. And what this means is if you actually make it to adulthood, which you're not likely to, but if you do make it to adulthood, you're going to live for a very long time. Let's look at these survivorship curves, look at the actual graph, and it makes more sense. Okay, so what we have in this graphic right here, this is percentage of surviving individuals, 100%, 100% down to 0%, and versus the percentage of maximum lifespan. So this is half lifespan, this is maximum lifespan. So let's look at the top survivorship curve. The top survivorship curve is current human model, and that is that at the time that you're born, you have a very low chance of dying. Most infants are going to survive. Please understand, this is actually only 20th century human survivorship curve. Pre-20th century, before 1900, even really before 1950, you expected to lose kids. People expected to lose half of their children before about 1900. There are some cultures they didn't even name kids until they were 2 because the chances of them surviving was that low. All right, modern human survivorship curve, very low infant mortality rate, very low mortality rate until you hit about half of lifespan. Average age of humans is average lifespan of humans. It depends on the country you live in. Let's just call it 80 for fun. 80 is about right. So half of average lifespan of humans is going to be about 40. Most people are going to make it to 40, and very few people will die. After about half lifespan, notice what starts to happen. You start to see individuals beginning to die. Once you reach close to that 80 mark, lots of people die. And so very little infant and adult mortality, very high elderly mortality. Type 1 survivorship curve. Type 2, birds, squirrels, they've got a type 2, and that is you really don't have any better chance of living or dying at any stage of your life. You have a pretty equal chance of getting killed. Remember, a squirrel is a prey animal, and they're going to be caught and eaten by cats and all kinds of other stuff. So that's why they have a high chance of dying. Our type 3 survivorship curve, this is an oyster. Most invertebrates, they have lots and lots and lots of babies, and very few of those babies are actually going to live very long. Most of them are going to die. So you have extremely high infant mortality rate. If you actually make it to, a year old, you're probably actually going to do pretty good. If you can actually make it to adulthood, you're going to live a very long time. Type 1, 2, and 3. Usually, type 1 survivorship curves are for those K-selected, those individuals that hover around carrying capacity. Type 3 survivorship curves are typically R-selected. They're opportunists. Once you have a big boom in a resource, lots of food available, lots of water, whatever, then they reproduce really quick. They have lots of babies, and the babies that they have, because there's a boom in resources, are going to have a good chance of surviving. But most years, they don't have that boom in resources, which means they still have lots of babies, but most of them die because there's just not enough to support. Life history strategies. The traits that will affect how fast a population is able to grow, traits that affect how stable a population is. It'll influence their reproductive schedule. One of the most important things is the first age of reproduction. How long is it before the individual is going to have that first baby or can have that first baby? And so K selected, generally they're going to have a much older age of first reproduction. R selected, much younger age of first reproduction. Remember, R selected are opportunists. When there's a big boom in resources, they can capitalize on it really quickly. So they're going to be able to reproduce very young, very early. The frequency of reproduction, how quick can they have another kid? K selected tend to be very long spaced, very long time between babies. R selected, very short time between babies. Having babies very quickly, as in like more than one group a year. What is humans? What is our usual not generation time? What is our usual age between kids? We have to go back into history and look at the average age between kids before birth control is really common. And when you do that, what you find is about 2 years. It's about 2 years between kids. So that's the age, the frequency of reproduction. So if a woman has a 30-year childbearing time, the numbers say she could potentially have about 15 kids if she's got 30 years and 2 years between them. Normal age of reproduction, not normal space of frequency of reproduction. Contrast that against, like, say, a rabbit. A rabbit can have like 4 litters of kits in a year, in a single year. And a rabbit can live, 2 to 3 to 5 years. So, and she can have 4 or 5 bunnies per reproduction. So now we're talking about a 5-year-old rabbit. She's had 4 litters a year. We're talking about 20 litters, 20 times 4, 80 kids in 5 years versus 15 kids in 30 years. How many babies are born at a time? Again, people. How many human babies are typically born per pregnancy? And 1 is usual. We just talked again about rabbits. How many babies does a mother rabbit have at a time? It depends on the species, but most of the time it's like 3 to 5. About 4 babies can she support at any one time. So K selected tend to have very few babies at a time. R selected tend to have lots of babies. Again, capitalizing on an unstable environment. Lots of resources, have lots of babies that will now survive because there's enough resources to support them. And then last is the amount of parental care. The amount of parental care, again, K selected tend to have lots of parental care. They tend to have very intense parental care. R selected tends not to have very much parental care. The babies very often are on their own. They're born, and so long, Junior. Good luck to you. K selected versus R selected. As we said, R selected are opportunists. They typically live in unpredictable environments. So we already talked about this. Terrestrial environments, land environments, are inherently more unpredictable than aquatic environments. We're going to find a lot more of these R-selected individuals on land, though there's still plenty in the water. They usually follow exponential growth curves, and then they have those sudden crashes that we talked about. They reproduce early. They have lots of babies. The babies they have are small. They mature rapidly, and they receive very little parental care. R-selected. They typically have very short generation times, and they have large brood sizes. All of these things we just talked about a second ago. Dandelions, mice, cockroaches, all of those things are all R-selected. Let's think and let's talk for just a little bit about how I could spend my reproductive energy. So imagine that I've got 100 energy units that I can use to put into the next generation. Well, how am I going to spend it? Well, one way is I could take all 100 of those energy units and put into one child. So how developed is that one child then when they're born? And the answer is, well, quite developed. If they got all of the energy that was available, that child can be a lot bigger. It can be much more advanced. It can be much larger. It can be much more able to take care of itself. The opposite end of the spectrum is I will have 100 kids and I will give them 1 energy unit each. How well developed are those kids going to be? This kid got 100 energy units to spend building its body. That kid got 1 energy unit to spend to build its body. They're going to be tiny. They're not going to have very many resources available to them, and they're not going to be very well developed, and they're not going to have a very good chance at being able to get their own food. And you can have all in between. You could have 2 kids, you get 50 each. I could have 5 kids that get 20 each. I could have 20 kids that get 5 each. 50 kids that get 2 each. How do you spend those energy units? How do you spend your reproductive energy? Do you have 1 kid that's really developed and you think, oh, well, I'm going to do the 1 kid that's really developed. I want my kid to have the best chance at survival. And what happens when you put all your eggs in one basket? What happens when that 1 kid, something bad happens, dies? Then where's your reproductive energy going? It is just gone. Versus, I got 100 kids. Well, yeah, and of your 100 kids, how many lived? 2. Okay, that's better than the 1 being lost. Are selected, which are they going to do? Are they going to do the 1 kid with 100? Or are they going to have 100 kid with 1 unit each? And the answer is they're going to be on that 100